It is the Gauss's law. It's a new kind of law that you will face. It is a new kind of way to calculate electric fields. So Gauss' law deals about to calculate the electric fields, not by just dividing the electric field electric charge distribution, some small dq's, and this is one way, but it deals about a different way of calculating the electric field by using some symmetry principles. That what these symmetry principles are, I will explain in this chapter. But we begin this chapter with a new concept, which is called the electric flux. Electric flux. What is electric flux? Elektrik akışı. The flux is something going in and out. Yes. Okay, so imagine, be quiet please, listen up. We have some electric field lines in some region of space, okay? And we have this surface, let's call a piece of paper or a handkerchief or whatever. We put into this electric field, and we observe that these electric field lines, of course, abstractly, which are crossing this region, right? And whenever you put a surface inside an electric field, these imaginary electric field lines will cross the surface, right? At some angles. So how do we characterize this number of crossing electric field lines to a surface, right? It depends on many things, when the orientation of the paper, the direction of the electric field lines, etc. But how do we calculate this? We have to define the flux, a new quantity in physics. What we do for this is the measure of crossing lines of electric fields, the area, right? Because it has some area. You have a larger area, you have a larger flux, because larger number of electric field lines will cross the surface. So for this, what we do is we just divide this surface into small pieces that we call dAs. Okay, this is again in comparison to these dx's, right? Small infinitesimal distances we call dx, dy, dz, whatever. But if you concern a surface, a two-dimensional area, then in that case these infinitesimal regions are the small areas, and we call these dAs. Okay. So let's imagine that we divide this surface, imaginary surface, not imaginary, of course we have a real, whatever you put in there, into small dAs. And these small regions, right, define vector. These small regions, which has some area which we call dA, they define a vector. And this vector is exactly perpendicular to these small areas. Okay, you just imagine this vector as this pen as a vector, and this is the surface. At every segment, this area vector is perpendicular to the surface. Okay, and we call this the vector dA, or this is normal. I call this normal. Normal vector. It's a unit vector, and this area is dA, and dA, as I said, has a direction which is normal to the surface, and the strength or the magnitude of this dA is just the area of the small region, and we define this dA vector times the electric field vector, which just crosses this area, the small area. You imagine this one small area is crossed by one electric field. And of course, depending on the orientation of the piece, the surface, the direction of the electric field will differ. Right? If you have this direction electric field, if I put this, the electric field will be almost perpendicular. But if I put this like this, the electric field will crosses this area at a different angle. Okay? So imagine the electric field crosses this area, and the electric field, the area vector is in this direction, because the area vector is always normal. right, is always normal to this small region dA, and this flux, the infinitesimal flux, is defined by, it's shown by d phi, and this d phi is just the electric field dot product with this normal vector, which is a normal unit vector to the small area surface, times the strength, the magnitude of this area, which we call dA, the small area. So this multiplication defines the infinitesimal flux through this infinitesimal dA area. Okay? And you see there is a vector multiplication in here. This vector E, because the electric field is a vector, dot product with the normal. And we all know the expression for this quantity, right? If you have two vectors dot product with each other, the result is the strength of the first vector times the strength of the second vector times cosine of the angle between them, right? You remember this dot product we have dealt with in work, right? In the concept of work in previous semester. The work was the F, the force dot product with dr, the length. So it's the same in here. Well, we call this the normal vector times with this dA as dA vector. Okay, as I said, this small areas defines a vector. This vector is always perpendicular to the small area, and this area is normal to the surface. And of course, the electric field need not to be normal at this point. Electric field may be in different direction. Okay. So as I said, the result of this dot product is just a number, because the dot product of two vectors is a scalar, and the flux is a scalar. It's not a vector. So it's just E times dA cosine theta. And the unit for the flux is, since we have electric field multiplied by area, the electric field has the unit of Newton per coulomb, and the area is meter squared in SI unit system. So the flux has a unit of Newton divided by coulomb times meter squared. So let's imagine, again, we have a uniform electric field, which is in the positive x direction. If you see this horizontal direction as x, we have a uniform electric field, and let's put a rectangular area, which is which makes the surface normal to the electric field. Okay, so there is an electric field like this, and we put a rectangular area like a piece of paper, a normal crossing the electric field lines, crossing normal the surface area. So what is the flux in that case? If you put the surface, the rectangular piece or paper like this, and the electric field is like this, what is the area vector of this rectangular region? It is normal at every point, right? And since the electric field also crossing normal, the rectangular region, the A area vector and the electric field is parallel to each other, right? Because if you put like this, at every point the area vector is normal to the surface, but the electric field is crossing the surface normally, so the area vector and the electric field is parallel, right? When you have two vectors which are parallel to each other, when you multiply them dot product, the result is maximum if they have no angle between them, or if they are parallel, because the angle between them is 0 and the cosine 0 is 1. Cosine 0 is 1, it is the maximum. So in this position, the maximum number of electric field lines are crossing the rectangular region, right? It is very intuitive, we can understand. But if you, well, I put this A vector in here, but if you put in this orientation, the a rectangular region, in this orientation, the surface is parallel to the electric field. But if the surface is parallel to the electric field, well, the surface is always having the normal vector in everywhere. Then the normal vector, the area vector, is always perpendicular to the electric field. As you see, if I put like this, the surface parallel to the electric field, the area vector is always normal to the surface. Since this is the area vector, and electric field is in the horizontal direction, the electric field lines and the area vector is perpendicular to each other, right? What is the result of dot product in that case? It is 0. If you have two vectors which are perpendicular to each other, then the dot product of these two vectors is 0. That means, with this definition of the flux, okay, the flux through this rectangular region in this orientation is 0. But this is very intuitive, because imagine this is a frame and there is a flow of air in this direction. Okay? If I put the frame like this, there is no any air flowing through this region, right? If I put like this, the flow is always parallel to the surface, so air does not crosses the frame. But if I tilt it like this, if I put this, and even make it the area vector parallel to the air flow, then I have the maximum amount of flow through the frame. Okay? The maximum amount of flow I have, in that case, the maximum flux. Because the area vector and the flow, the velocity vector of the flow of air is parallel to each other. And two vectors parallel to each other multiplied dot product, which has the maximum. If I put like this, there is no. If I tilt it like some angle, which is this case, and this angle is theta, as I said, the area vector is always perpendicular to the surface. Whenever I tilt the surface, the area vector is changing. Okay, the area vector is changing. Of course, the area vector is changing, and it is changing its angle with the electric field, because the electric field is always in this direction. So, in that case, I have some amount of flux through the region, rectangular region, but it's not maximum or not minimum. So the amount of the flux is completely determined by, in each case, in the first case, since E and A are parallel to each other, and there is no angle between them, there is 0 angle, cosine 0 is 1. So the flux in that case, E times A, the strength of the electric field times the total area of this region. In here, the flux is 0, because E dot A is 0, not because E is 0 and the A is 0, but because their angle between them is 90 degrees. Nor E in this position or the area vector is 0, but their angle is 90 degrees and the dot product is 0. So the flux in that case is 0. But in here, the flux is just the strength of electric field times the area A times cosine of this angle theta. And if you increase this angle, you decrease the flux, of course, because cosine, when you increase the angle, decreases. So I think this is understood, this flux concept, and without understanding this flux, it is not possible to understand what the Gauss's law is. Okay. So far, I have concern only the open surfaces. What I mean by open surface. This is an open surface. Okay. Open surface has a border which has a curve, a line. For example, for a rectangular region of space, the border is just a rectangular line, right? It's these lines. But also you have closed surfaces. For example, the surface of this bottle. It's a closed surface. It's closed surface, it divides the region, the universe, into two regions. One is inside, the other is outside. Right? There's inside and outside. For closed surfaces, you can always divide the universe into two different regions. But this is not the case for an open surface. open surface does not divide the universe into two regions. And the closed surface, does a closed surface have a border? Sınır. Dünyanın sınırı var mı? Do we have any edge or border on the surface of Earth? If you go border, if you go in one direction on a closed surface, you always circle it. There is no any edge, right? And even if there were nothing on the surface of Earth, no mountains, no oceans, nothing. If you go in one direction, you don't know how long are you going or where are you going, because you end up with the same thing always. There is no any border. So there are differences between the closed surfaces and open surfaces, and of course we can also define the flux through a closed surface. Okay, it is possible to define for a flux through a closed surface. Imagine a sphere, right? In that case, what is the area vectors for a closed surface? What are the area vectors? If you just concentrate on one region, let's concentrate on this region. As I said, the area vector is always perpendicular, right? As you move along, the area vector will also change, will rotate. But everywhere it will be perpendicular to the surface. At these edges, for example, like this. Here it is like this. Okay. For closed surfaces, the area vector cannot be toward inward. It is always outward. Okay? This is the rule. The direction of the area vector for closed surfaces is always out of the surface. Okay? It points the out always. This is the rule. And this is the just convention. You like it or not. So there is only one determined direction for the area vector. It is always outward. Yes. If this surface is rough, roughness is not infinite. It has ups and downs, whatever. Okay. In these small ups and downs, again the area vector is changing, but always it is perpendicular to the surface. Okay. So this is what I was trying to tell you, that the area vector, for a closed surface, just divide the surface into, again, small pieces of dAs, and these dAs are vectors, and they are always outward. So we denote the total flux through a closed surface by this integral. Okay, and this integral has a special name. It's a surface integral. And you see that this integral is a double integral. But this is just a symbol. If you have this closed circle in an integral, that means the integration region is a closed surface. Okay. Whenever you see this circle right in the middle of the integral sign, that means you are taking the integral over a closed surface. Okay. Well, we will see these. An example, and we want to find the flux through a perfect sphere. Okay, let's imagine we have a sphere, and let's put a charge Q just in the center of the sphere. Okay, this charge creates a field, right? It creates a field, electric field, and this electric field is at every direction, right? You know that the electric field is pointing in every direction radially. We call this radially outward. We also let's think that this surface of an imaginary sphere, okay, and let's think that this sphere has on the surface small areas that we call dA. As you move along as you move around the sphere, on the surface of the sphere. This area vector is going like this, right? It's always perpendicular everywhere, and it is always in the direction on the line which crosses the center, right? It's always the direction line is crossing the center. That's very easy to understand. Well, as I said, this Q, the charge, also creates electric field, right? And remember, the electric field, because of a charge, this is plus charge Q, it's always out from the charge. If this is a plus charge, and it is symmetric, spherically symmetric, right? If you move along a circle which has the center at the center is at the charge position, and at every point on this circle, the electric field, when you move along the circle, electric field looks to you just the same, right? Wherever you go on the surface, the electric field line always going out perpendicularly from the surface, right? Explaining the same thing in Turkish. Yüzey üzerinde nereye giderseniz gidin, aynı elektrik alanı göreceksiniz, değil mi? İster kuzey kutbuna gidin, ister güney kutbuna gidin, ister ekvator bölgesinde dolaşın, elektrik alan her zaman yerden dik olarak çıkacak. Yani simetrik, hiçbir zaman değişmiyor. Nereye gidersem gideyim, aynı elektrik alanı görüyorum. Okay. That means the electric field lines and these area vectors kabus gibi. Okay, so the electric field lines and these area vectors at every point on the surface of the sphere is parallel, right? And the dot product never changes at any point. At any point, the dot product with this electric field lines, electric field vector, and the area vector is always the same, because they're always parallel. Wherever you go, both the electric field line and the area vector crosses the surface perpendicularly, and they are in the same direction. So can we calculate the flux then? Okay. So let's imagine that the sphere has a radius capital R, and this small r is the unit vector pointing in the direction of electric field. So the flux is just the electric field times the area vector. And the electric field, let's put the electric field now input in this position. What is the area of a sphere having the radius r? 4 pi r squared, you already know, it's from geometry. And what about the electric field at a point which has a distance r from this point charge q? What is the electric field? If you have a point charge and some point P which has a distance r to the point charge, what is the electric field? K times Q divided by R squared. Okay, let's put these two also. But we always write, we sometimes write this K, Coulomb constant, as 1 over 4 pi epsilon 0. This is just, sometimes we use K, sometimes we use 1 over 4 pi epsilon 0. Epsilon 0 is another physical constant. So let's put also this electric field, E, in this equation. and this is the electric field, and multiplied by let's multiply these two by the area, 4 pi r square. So what do we have? We have this 4 pi here and 4 pi here. They cancel out, right? And also we have r square here in the denominator, but in the surface expression we have also r square. They cancel out. So we are left with the charge q divided by epsilon 0. So the result of this electric field created by a point charge q, which is located on the center of a sphere having a radius r, is the flux is just the charge q itself divided by some physical constant epsilon 0. Does it depend on the radius, the result? However, this sphere, you make it larger or smaller, the flux is the same. It does not change. It does not depend on r, the radius, and even it does not depend whether the sphere of a surface, the surface of a sphere is perfectly symmetric or some irregular shape. It doesn't care.
But if it's an irregular shape, also the area will be different.
Well, the area will be different, but the portion that it has these irregularities will be closer to the center, right? Some points will be close, some points will be large, and also at every point for this irregular shape, the directions of the electric field and the area vector also will be different. They will be not parallel to each other for irregular shaped surfaces, but we don't care about this product because the result does not depend on the shape or the radius or the largeness or the smallness of the closed surface. Whatever the closed surface is, this flux will always be the same. So this is very important observation. It does not depend on geometry. Whether you put this charge inside an irregularly shaped surface, you don't care, whatever, but the only requirement is it should be a closed surface. It's dividing the universe into two regions, inside and outside. If you put the charge inside an irregular shape, any closed surface, the result will not change because the result does not depend on the geometry, right? This may be an awkward result for you. It may be difficult to realize, but it's so. So, okay. At some regions, this electric field and the area vector, for example, let's take this point, okay? This point. This point. In this point, the electric field vector is always outward, but at this point, the area vector, dA, is not parallel to the electric field, right? Like this. But we don't care, and if you sum, because the result of this integral is the sum. We have many contributions at every point on the surface. At some points, the electric field has a larger angle between the area vector. At some other points, it is parallel. At some points, for example, this point is closer to the center, so the strength of the electric field at this point is larger than the strength of the electric field at this point. So both the directions of these electric field lines and the area vector lines and their strengths are changing, but the result of adding them is not changing. It's always fixed. The result is just Q divided by epsilon 0.
The result of what?
The flux. The flux does not change. Okay? At every point, we multiply the electric field, strength and direction by the area vector and add them at every point. So this totality is not changing. Okay, so what the Gauss law says? The Gauss law says that for a closed surface, whatever you have inside the charge, the flux through this surface is always the charge inside divided by epsilon 0. This is the Gauss law. If you have a closed surface, okay, you may have some number of charges, not only one charge. Some charges might be positive, some charges might be negative. And the flux through this such closed surface is always the total charges divided by epsilon 0. But if you have a plus charge and a minus charge which has the same strength, what is the flux then? If you put two charges and they have the same strength but opposite signs, what will be the flux?
1?
It is 0, right? Why? Plus charge will produce an electric field which is out, but minus charge will produce an electric field inward. If you have an inward vector electric field and outward the area vector, since the angle between them is a wide angle, their dot product is negative, right? But for the ones produced by the positive charge, the angle between the area vector and the electric field is a narrow angle. The cosine of that angle is positive. But for the ones which are produced by the negative charge, the angle between the electric fields and the area vector is wide angle. The cosine is negative. So these, and you add, make it 0. If you have the same strength, of course. Okay? The flux is not vector. It's scalar. It's always scalar.
So you cannot say it's cancel each other.
Well, I didn't say that the flux is always positive. Well, I said the flux is a scalar, but it may be negative also. Right? So, for example, if you think the previous case, let me show you. Well, imagine you put in here not the positive charge, but the negative charge. That produces the electric field just in the reverse direction. So when you multiply this, E dot A, since cosine 180 degrees is minus 1, this multiplication will be minus E times 4 pi r square. So you will have in that case a minus flux, a negative flux. So the flux can be negative. If you have field lines toward inward to the closed surface, you have a negative flux. Outward with a positive flux. Alright, so the Gauss's law says, however the number of charges are, we don't care. Just add these charges and divide it by epsilon 0. If they are inside a closed surface, this is the flux. Okay? Alright, so an example. Suppose you have a surface S, but you just see the cross section. It looks like a curve, but it's a surface. Okay? We see a cross section, and you put a charge on inside it, a plus Q charge, and of course it will produce some field which is toward outward. So if you want to calculate the flux through the surface S, and without considering about what is this dA, what is E at every point, you don't deal with that. You just write down this integral as a symbolic integral, and you know the result. Okay, the result is just Q divided by epsilon 0. You don't have to calculate electric field at every point on the surface to get this expression inside the integral. Just you don't do that. You don't need to do that, right? The result, the sum of the integration is already there. It's Q divided by epsilon 0. Well, if you put one more charge, which is negative, then it will, as I said, produce a field which is inward to the closed surface. That means the electric field vector times the area vector is always negative because they are wider angle. So it will cancel out. With the plus side, you have a 0 flux. So in this example, if you put plus Q and minus Q inside the surface, then you have a 0 flux. Let's imagine these surfaces crossing each other. They have some common regions, whatever. Okay, and you put some charges, in some regions. Okay, just to make some exercise for you. So suppose these point charges are all the same in strength, but the red ones are positive and the blue ones are negative. So we have this S1, this surface, and this is S2, which is this one, and this S3, which is this one. Somehow they have some common region. Right? We don't know how, but they have common region. So what is the flux through surface S1? Why? Because it has 2 negative charge in equal amount and 2 positive charges in equal amount. So it is 0. You put total 4 charges, of course, yeah, 0. What about S2? In terms of Q and epsilon 0? For Q, because they all have positive Q charges, 4 Qs, and just divide this total charge by epsilon 0 to find the flux. And what about S3? The flux through S3? It has 3 minus charges and 2 plus charges. In total, it has minus Q divided by epsilon 0. So it's easy. As long as you understand this flux thing, and it is easy to calculate the flux. Now let's calculate the electric field inside and outside of a spherical shell by using the Gauss law. So let's imagine we have this spherical shell. You're seeing the cross section of it, and the shell has a radius of r, and let's imagine that it is uniformly charged over the surface, and the total charge is Q. So first begin with an inside point. You choose any point inside the shell, and the question is, what is the electric field in here? So in applying Gauss's law, we pick up some Gaussian surfaces, imaginary Gaussian surfaces, which fits to the symmetry of the problem. So as you see in here, the symmetry of the problem is spherical, contains the spherical symmetry. Because we might choose this point anywhere on this imaginary surface, which has the same distance to the origin. Okay, suppose this has a distance r1 to the origin, and if we want to find the electric field at that point, this point, you might as well choose the point like here or any other point, and that means wherever you go on this Gaussian surface, there will be no any difference, because wherever you go on this surface, you will see exactly the same charge distribution. So either you choose this point, or any other point on the surface, it doesn't make any difference. Next, what will be the electric field at these points? Okay, so let's first consider the point in question. The electric field direction might be radially inward or radially outward. Okay, there is no any other directions, again, because of the symmetry of the problem. If the electric field was pointing in a direction which is not lined up with the center, then it would violate the spherical symmetry. And just think about it. So then the electric field will be either outward or inward. The next thing is, we will calculate whatever the direction of the electric field is, inward or outward, what is the flux of this electric field through this imaginary Gaussian surface. Let's label this Gaussian surface y1. The next thing we should consider is what are the area vectors on the surface. Since the surface is a sphere, and on a surface the area vector must always be perpendicular to the surface at every point, then the area vectors at every point, the area vectors dAs at every point on this imaginary surface must be radially outward. Okay. So the next thing is, once we have set all the vectors, then the electric field directions and the area vector, we will calculate the flux through this imaginary surface. Let's call this phi1, and this is the integral over the surface 1, the Gaussian surface 1, and it is E dot dA. Well, since at every point, if the electric field inward or out, let's choose the electric field direction as outward, let's choose that way, and we will see that the result will not change. If the electric field is outward and the dot product of the electric field at every point on this surface will be constant, because at every point the dAs, the area vectors and the electric field vectors are all lined up and they're parallel. Okay, so this integral will be just constant E times A, and we know that the area of all the sphere, the surface of a sphere, is nothing but a 4 pi r square. R is the distance here to the origin of this original point. So the flux through this surface, we don't know the electric field is, just electric field E times 4 pi r square. Next, what the Gauss law says, that this flux must be equal to, the flux through the surface 1 must be equal to the charge inside the surface divided by epsilon 0. So let's see, what do we have inside this Gaussian surface? We have nothing, because all the charges are distributed over the outer spherical shell, and we have nothing inside this surface, the Gaussian surface 1. So this should be 0. That means the flux calculated in the first line is equal to 0. So since the area cannot be 0 because we have a non-zero Gaussian surface, the only way is the electric field through this surface at every point must be equal to 0. Okay? So the result is, if you are inside a spherical shell which has the charge, all the charge is uniformly distributed over the shell, the electric field at any point inside is equal to 0. So this is this may sound counterintuitive, but when you think it about carefully, wherever the point you choose, okay, if you think all the sections, all the small parts of dQs over the surface will contribute to the point because of the Coulomb law, and this contribution, the vectors contribution, electric field contribution of all the segments will cancel out. Okay, so anyway, this is the very short way, but you should bear in mind that the charge distribution should be uniform. If the charge distribution is not uniform, for example, if there are some charges over some region of the spherical shell larger than the other part, then you wouldn't have this result. The result will be a non-zero electric field, because in that case there will be no spherical symmetry in the problem, because wherever you go you wouldn't see the same charge distribution because the charge is not uniform. But this is not the case in this problem. So let's move on with the second part of the question. What is the electric field the outside of the spherical shell? So let's again pick up any point outside the shell, and what we do is just we choose an imaginary Gaussian surface, just passes through this point in question, and of course the surface should contain the symmetry of the problem, and there is only one symmetry of the problem, which is the spherical symmetry. Then this surface should be a spherical surface. You shouldn't take a rectangular box or something else. Alright, so let's label this surface as the Gaussian surface 2, and again, any point on this Gaussian surface will be exactly similar to the point in question originally, because wherever you go on this surface you will see the same, exactly the same charge distribution. So that's why we choose this spherical surface, because the spherical surface outside has the perfect spherical symmetry. Wherever you go on this surface you will see exactly the same charge distribution here. Alright, so what about the direction of the electric field? Of course, the direction of the electric field, just because of the intuition, it would be outward, because there are positive charges inside, and from the positive charges, the electric field is always go outward. Alright, so you can again see that these electric field lines will be outward at every point on the surface, and at every point on the surface the electric field lines will be perpendicular. Okay, what about the dAs, the area vectors? Again, since this is a spherical surface, at all points on the surface these area vectors will be radially outward. Okay, so again, at every point the electric field lines and the area vectors are parallel to each other, and they are all perpendicular to the surface. So it's very easy to calculate the flux again. The flux through the surface 2 is exactly the same. It is just the electric field strength times 4 pi r2 square. R2 is the distance from the origin to the or the radius of the second Gaussian surface. So the Gauss law says that this flux is nothing but the charge inside divided by epsilon 0. This flux is equal to the charge inside of this Gaussian surface divided by epsilon 0. But the charge inside is just the total charge, which is symmetrically distributed over the spherical shell, and this is equal to Q divided by epsilon 0. And the rest is just equate these two lines for E times 4 pi r square and to Q divided by epsilon 0. And if you solve for E, the strength of the electric field, the result is nothing but the electric field of a point charge where it seems like all the charge, which is symmetrically distributed over the spherical shell, as if it is concentrated on the center, right? Because the electric field is just K times Q divided by r square is nothing but the electric field of a point charge. The result is very interesting. So at any point which has a distance r to the center of this spherical shell has the electric field exactly equal to the charge, the point charge, which is all concentrated on the center, and divided by this distance squared. So this is the way how to calculate the electric field inside and outside of a spherical shell. Now we have a charged plane and it extends to infinity in every direction. And suppose we have the charge density sigma and it is uniform, it is a constant over all the plane, and we are interested in finding the electric field at a point which is a distance, perpendicular distance d, away from the surface of the plane. So again we will choose a Gaussian surface, and this time, since the symmetry has planar symmetry, we will choose the planar Gaussian surface. In fact, we will choose a pillbox which has a finite volume. So this pillbox is a rectangular region of space, and it cuts through the planar charge distribution and it extends to the other side. And since we want this region symmetric around the charge distribution, so we should take also the down region as our part of the Gaussian surface. So this is the Gaussian surface, and the next thing is we will calculate the flux through the surface, and we will be able to express this flux in terms of this electric field at the point in question, and we will use some symmetry arguments, of course. And symmetry argument says that since the planar charge is a positive charge, then it is very obvious, very intuitive that the electric field will be in the direction which is perpendicular to the surface of the charge distribution, because the electric field is always pointing outward from a positive charge. That means that will make much of the things easier in calculating the flux through this rectangular region, because choosing a point on this top surface of the Gaussian pillbox at anywhere will not make any difference in the strength of the electric field, because wherever you go on this top surface of the Gaussian pillbox, it will have a same distance to the charge distribution. So wherever you go, you will see exactly the same charge distribution. Since there are no edges of the plane, it is an infinite plane. Wherever you go on this parallel surface of the top of the Gaussian pillbox, you will see exactly the same charge distribution. That means at any point on this top surface, the electric field will be the same. So this is our symmetry argument. But on the other side, at the down region, again, any point on the bottom surface will see the same charge distribution, and the electric field will be pointing downward, of course. So we will come to this point in short. Alright, so on the top, the electric field is away from the surface upward, and on the down, the electric field is in the downward direction. Alright, so maybe it is better to picture this distribution from a side view, and the cross section will just look like this. We have this charge distribution, and this line represents the plane, and the plane is perpendicular to the surface of the board, and this is our rectangular pillbox. Okay, so the electric field is up in the upper region, and it is down in the down region. So what about the area vectors of these pillbox? The top surface, of course, since the area vectors will always be perpendicular to the Gaussian surface, closed surface, the top surface will have the area vectors which is in the upward direction, which is parallel to the electric field. And in the side surfaces, since the area vector is always be perpendicular to the surface, it will be in this direction, for example, to the right surface, and in the left surface, the area vector will be pointing in this direction to the left. So at the down surface, of course, bottom surface, the area vector is again parallel to the electric field in that region. Okay. So let's label the fluxes through these surfaces. Let's label the top surface, the flux of the top surface phi1, and the flux through the bottom surface as phi2, the flux through the side surfaces phi3 and phi4. Well, since we have 6 surfaces, I just didn't show you the rest of the surfaces because they will be parallel to the surface of the board. Anyway, because of the directions, you can easily realize that the flux through the surface, the side surfaces, will be equal to 0, because the on these surfaces the electric field and the area vector are all perpendicular to each other. So the dot product of them is equal to 0. But on the bottom and top surfaces, since the area vector and the electric field vectors are in the same direction and they're all constant through the top and bottom surfaces, it will just be the electric field times the area of the top or bottom surface. So let's call A as the area of the top or the bottom surface, because since it's a rectangular region, a rectangular box, these surfaces will be equal to each other, and let's call one of them is A. So the total flux, of course, will be the sum of all fluxes, and this is phi1 plus phi2, and it is 2 times the electric field strength E times the area of the one of the top or bottom surfaces. Well, from now on we will apply the Gauss's law. The Gauss's law says the flux through any closed region of space is equal to the charge which is located in that region divided by epsilon 0. So the question in here, what is the charge inside this rectangular box, the Gaussian pillbox? Well, it's very easy, because the cross section with the rectangular box and the planar surface is just this square, or whatever you call it, because it may be a rectangular surface or a square surface in here. Well, this area again, as you see, since this is a rectangular surface, it will be the same area A with that of top or bottom surface. So the question is, what is the total charge of this region, because this is located inside the rectangular box. And it's very easy, because since we are given the charge density, surface charge density, to find the total charge is just multiply the surface charge density with the area, right? So Q in is nothing but the sigma times A. And the next thing is we equate these two quantities. On the left hand side we have the total flux, on the right hand side we have the total charge divided by epsilon 0. So from this equation it is very easy to get an expression for the strength of the electric field, because we cancel out on both sides the A's and the areas, and we reach the result. The strength of the electric field is equal to sigma divided by 2 epsilon 0. So the strength of the electric field, as you see, does not depend on the distance of the point from the surface. It's very interesting. It does not depend on the distance. Well, it seems a counterintuitive argument, because well, you will think that when you come close to the surface or charge, the electric field strength will be large. But imagine if you are yourself on this point, and if the plane extends to infinity. So wherever you look, whichever direction you look, you will see exactly the same charge distribution, whether you are close to the surface or not. You will see exactly the same charge distribution. So because of that, you might maybe understanding or realizing that the electric field strength will not depend on the distance. Alright. So the immediate consequence of this is, let's imagine we have two planar surfaces, okay, just like we had in the example. One is having a positive surface charge density, and parallel to it we have another parallel plane which is large again, but this time it has a negative charge density. So we have two planes, one is plus and the other has minus surface charge density. But the question is, okay, they have the same strength of the surface charge density. Okay, so this is the example. Alright, so To calculate, the question is, what is the electric field in between these two planes? Okay, or let's say in every point, every region. So we have three regions. We have top of the plus surface charge density. We have the region in between these two planar surfaces, and we have the region which is down to the minus surface charge density. Let's write down the electric fields around the total electric field on these three regions. If you think the top region of the plus surface charge density, we have, let's label this E plus, the electric field, and because of the same surface charge density, plus surface charge density, the region in between will have a downward electric field produced by the positive surface charge density. And since downward in everywhere, because of the plus surface charge density, the electric field will be in the same direction. It is the same electric field and it's the same strength, because again we are imagining that these surfaces are very large and the electric field strength does not depend on the distance. So let's do the same for the negative surface charge density, because at the end we will superpose the electric fields. For this region, the electric field, because of the negative surface charge density, will be downward, and in between again it is downward because it still we are on the top region, and at the down region, at the very bottom region, the electric field, because of the surface charge density, will be in the upper direction. So if you superpose these electric fields at every three region, and you will see that the top region of the plus surface charge density will have two electric fields, but they are opposite to each other. So they will cancel each other because the strength of the electric field is the same, but they are in opposite direction. And it is the same for the very bottom region. The electric fields are in the opposite directions in here, but in between the electric fields produced by both planes are in the same direction. If you add them, you will have 2 times the sigma divided by 2 epsilon 0 will give you sigma divided by epsilon 0 as the electric field strength between two planes which are oppositely charged of same strength. Okay, so this is an immediate application of the planar charge distribution, planar symmetry of Gaussian law for calculating the electric field between two oppositely charged planes. Now suppose we have a charge density over a line, and this line extends to infinity, and suppose the charge density is plus, and we call this lambda as the line charge density, and we are curious about the strength of the electric field around this line. So let's choose a point, and we want to find the strength of the electric field at that point, and we will now use the Gauss's law to calculate the electric field, not the Coulomb's law, because we have a kind of symmetry in the problem. And as you see here, you choose this point which is a distance r, perpendicular distance r to the charge distribution. If you will pick up this point like around here, or the top surface which has the same distance, it will not make any difference. So wherever you go parallel to the line, the charge density along this line, the electric field exactly would look like the same. So this imposes some kind of symmetry, and this time we have to choose a Gaussian surface which reflects this symmetry of the problem, and the best choice for this is to choose a box again, but this time the box is a cylinder. and the cylinder, the axis of the cylinder contains the charge distribution. So wherever you go on this hypothetical surface, the Gaussian surface, on the side surface, the strength of the electric field will exactly be the same. So let's give some dimensions to this surface. Let's take the height of the cylinder as d, and the next thing is to do, of course, we will calculate the flux, the electric flux, through the surface of this pillbox, cylindrical pillbox. Okay. So to find this, again, we have to determine the area vector at every point of this surface. And for example, if you have chosen the small area right on the side surface of the cylinder, and this area vector, of course, will be radially outward. So when you think that the electric field through this all the small areas, dAs, you will recognize that the electric field also should be in the same direction, because the electric field is always away from the charge, away from the positive charge, and you easily recognize that the electric field at every point of the side surface of the cylinder, the electric field and the area vector is always lined up and it's parallel to each other. Alright. What about the bottom and top surfaces of the cylinder? Of course, we need to take these surfaces into account to calculate the flux, because in every Gaussian surface is a closed surface, so we have to consider all the surfaces of this pillbox. Well, as you recognize easily that the area vector on the top surface is in the upward direction, and this similarly the area vector at every point on the down surface will be in the downward direction, and the electric field at these points, at every point on the top and bottom surfaces, will be perpendicular to the area vectors. So you can easily now say that the flux, electric flux through the top and bottom surfaces will be zero. So the only non-zero part contribution will come from the side surface. Okay, let's call this flux phi1, and the top is phi2 and the bottom is phi3. So phi2 and phi3 is 0 because of the perpendicular directions of electric fields and the area vectors. And what about the flux through the side surface? So the expression for this is E times A, because at every point the electric field and the area vectors are parallel to each other, so this dot product is always the constant. So you can immediately write down, instead of an integral, write down this expression for the flux, the strength of the electric field times the total side area of the cylinder. Okay. So next, you can explicitly write down this side area in terms of the distance to the point in question, which will be the radius of the top and bottom surfaces. And the side surface is nothing but the length of the side surface, which is just the circumference of one of the top or bottom surfaces, times the height. And so this is the simple expression for the area of the side area of the cylinder. Next, we will apply the Gauss's law, since we already determined what the flux is, and the Gauss's law says this flux must be equal to the charge inside divided by epsilon 0. So the next question is, what is the charge which is located inside this Gaussian pillbox? So the total charge inside this Gaussian pillbox will be calculated by multiplying the charge density with the length of the line charge, which is located just inside this Gaussian pillbox. So it's again easy. It is just lambda times d, because the length which is located inside is just d, and epsilon 0. So the next thing is to equate these expressions to each other to find an expression for the electric field. And you can easily solve for E, having the electric field as the line charge density divided by 2 pi times epsilon 0 times r, which is the perpendicular distance of the charge density to the point in question. So as you see, when you go away from the source, the line charge, the electric field drops as 1 over r. And this is 1 over r expression. Remember, the electric field was dropping as 1 over r square for point charges, but it is not the same for a line charge. It is different. And if you compare this to the planar symmetry, as you remember, the electric field was not is not depending on the distance from the surface, and it's always constant, but it drops as 1 over r for a line charge, and it drops as 1 over r square for a spherically symmetric charge or point charge. Alright, let's draw the electric field strength with respect to the distance r, and it is nothing but this 1 over r curve. As you go away from the origin or the line charge, the electric field will decay as 1 over r. In this example, we have a non-conducting solid sphere, and it has a charge of Q. It is distributed over all the volume of the sphere, and the sphere has a radius A. So the question is, what is the electric field anywhere with this charge configuration? So we will first consider the point inside and outside of this solid sphere. But before that, let's express the charge density of this non-conducting solid sphere, because we will need this charge density to apply the Gauss's law. So simply, the charge density is nothing but it is the total charge divided by the volume of the sphere, and the volume of the sphere is in 4 pi a cubed divided by 3. So let's pick up a point inside the sphere, and it has a distance r to the center, and the question is, what is the electric field here? So unlike the example of a shell charge, the electric field inside this sphere will not be zero if you think, because there are charges distributed everywhere in the sphere, not like the spherical shell, which is the charges only located on the shell. To solve this problem, again, we will first decide the symmetry of the problem, and it is very obvious that the symmetry is spherical symmetry, because if you think this point, another point which has the same distance to the origin, for that point also, the charge distribution inside will look like the same. So wherever you go on a hypothetical Gaussian surface inside the sphere, having a radius r smaller than a, the surface of the sphere will be symmetric in terms of the strength of the electric field. So let's pick up this hypothetical Gaussian surface. It's a spherical surface inside this solid non-conducting sphere, and as I said, any point on this surface, because of this spherical symmetry, will have the same strength of electric field. Alright, so the other thing is, okay, then what will be the direction of the electric? Let's choose the direction as radially outward, okay? Because again, because of the symmetry arguments, the direction at that point will be either inward or outward, but since we have positive charge distribution inside, this will be outward. And the next thing is, what is the area vector at each point? So just like we had done this experiment, the example of spherical shell, the surface of a Gaussian surface of a sphere has the area vector all perpendicular to its surface. So the area vectors on the surface and the electric field will exactly be parallel at every point. So this will ease our calculation of flux. So once we have chosen the surface, the next step is to calculate the flux through the surface, and the flux again will be constant, just the electric field strength on the surface of this Gaussian sphere times the Gaussian spherical surface's area, A. So this is the result of the flux. The next is, well, we can write down explicit expression for the area at 4 pi r square anyway, but we don't know the strength of the electric field, so it is as it is, like E. And the next thing is we apply the Gauss's law. The Gauss's law says this flux must be equal to the charge inside this Gaussian surface divided by epsilon 0. So the next step here is to determine the charge which is located inside this hypothetical Gaussian surface. Okay, not all charge, but only we are interested in the charge which is located inside this spherical region. So it is obviously nothing but the charge density times the volume occupied by this hypothetical Gaussian surface. Okay, so let's express this: the charge density times the volume of the sphere which has radius r, and we know that this charge density is the total charge divided by the total volume. So this charge inside is proportional to the volume of the sphere which has radius small r divided by the volume of the sphere which has the radius a. So it is simply expressed as q times r cubed divided by a cubed, because the volume is always proportional to the radius cube. So this is the total charge inside this Gaussian surface. So the next is just you equate these two expressions, E times 4 pi r square, to this expression with explicitly depending on the total charge Q and R of the distance of the point to the origin in question, and in terms of the A of the original sphere's radius. So if you put everything and solve for E, you will find that the electric field strength is Q divided by 4 pi epsilon 0 times R divided by A cube. So it's an interesting result because the electric field depends linearly on the distance R to the origin. So if you increase this distance, if you pick up a larger inside sphere, and the electric field through that surface of the sphere will be larger, okay, because everything else is constant and it is proportional to R. So as you go away from the center, the electric field strength will get larger, because as you go away from the center, the sphere will contain a larger charge, so that will increase the strength of the electric field. Well, right on the surface, with this result, right on the surface of this non-conducting sphere, the electric field will be equal to Q times K times this 1 over 4 pi epsilon 0 is K, A which is the radius of the non-conducting sphere divided by a cube, and 1 over a square. So right on the surface it is q times k times 1 over a square. Alright, so as if all the charge is concentrated on one point in the center. So let's move on with a point, picking a point outside the sphere, and again we will do the same tricks. We will choose a Gaussian surface that passes through this point, and again let's choose the radius of this outside region is r, but this time small r is larger than a. So again everything will be the same. The electric field through this hypothetical surface will be parallel to the surface's area vector at every point. So the flux again is E times A, and A is the total area of the spherical surface, 4 pi r square, but again r is this time larger than small a. Alright, so the trick is, if you apply the Gauss's law, this flux is equal to the charge inside divided by epsilon 0. But this time the charge inside is simply the total charge of this non-conducting sphere, which is nothing but q. Then we put this on the right hand side of the equation. You will get this expression, and it is easy to solve for E, and E this time is k times q divided by r square. So as you move away from this origin, if you are outside the sphere, then the electric field will fall as 1 over r square, which is exactly the same with that of a point charge. So this is not a surprising result. We have done this for the spherical shell too. If you are outside the spherically symmetric charge distribution, then the electric field at that point is nothing but as if all the charge is located at the center. Okay, so we recover the same result with that of a point charge. If you draw the electric field strength with respect to r for this problem, then until r is equal to a, the electric field inside linearly increases as you move away from the origin or away from the center of the sphere. But right after the surface, the electric field will decay, will drop as 1 over r square. So this is the graph of the strength of the electric field for a non-conducting solid sphere which has a uniform charge distribution all over the volume. Let's think about the conductors in electrostatic equilibrium. What we mean by this, we will analyze the motion of free charges inside the conductor which are in electrostatic equilibrium. And we will take metals as conductors. Then the first statement that if a metal or a conductor is in electrostatic equilibrium, that means at every point or inside the conductor, the volume of the conductor, the electric field must be equal to 0. So we have this conductor, and this gray region is the volume of the conductor. And think about the counterintuitive argument that the electric field is not equal to 0. So imagine if inside the conductor the electric field is not equal to 0. We have then, for example, the electric field lines, and the property of the conductors is, why do we call the conductors? Because there are free charges moving inside the conductor. So if the electric field is not equal to 0, then the free charges, the electrons inside the conductors, because of this non-zero electric field, will move. So if there is a non-zero electric field, then that means the sum of the electrons that see these non-zero electric fields will move. But this is in violation that the conductor is in electrostatic equilibrium. What we mean by electrostatic equilibrium, it is that all the charges, all the free charges must be in steady state, must be in motionless state. So this violates, if there is an electric field inside the conductor, this violates the equilibrium condition that the charges must stay at rest. So the statement is that the electric field must be equal to 0 inside everywhere the conductor. So we have E is equal to 0. And what happens if we charge a conductor, if we put extra charges, okay? If we put extra charges, let's say if extra plus charges, where do these charges go? Do they distribute themselves everywhere uniformly inside the conductor, or do they go anywhere else? So imagine these extra charges, take two of these extra charges inside a conductor, okay? Even if, by the way, even if we charge a conductor for a very short amount of time, typically this is in the order of nanoseconds, once you charge the conductor with extra charge, again these charges will distribute themselves on or inside the conductor, so that all the charges will be at rest. After a very short period of time, even if you charge the conductor will reach the electrostatic equilibrium condition in a very short amount of time. So imagine two of these charges is going inside the conductor like this, having some distance in between them. But the thing that if you think these two charges, then because of the electrostatic force between the like charges, they will repel each other, and they will repel each other until they are at rest. Okay, so that means in electrostatic equilibrium, because of the forces that moves the charges all the time, in electrostatic equilibrium, the charge cannot go inside. Otherwise, if they go inside somewhere, then they will feel their electrostatic force, repulsion force, and they will move in opposite direction. But this again violates the condition that the charges should be in electrostatic equilibrium. So that means the charge, somehow they will distribute themselves on the surface. Okay, because on the surface, on the boundary, there is no any place to go, there is no any room to move anymore, and they will be outer surface, they will be residing, or they will be localizing themselves without motion, without moving, on the outside surface of a conductor. If the conductor has a volume, then this is the case. Even if the conductor has some cavity inside, this is the same situation. But what happens to the inner surface, we will analyze this later. Okay, so by this simple argument that if there is an extra charge inside the conductor, on the conductor, and these charges must locate themselves on the outer surface, we will prove this result by using Gauss's law like this. Let's pick up an imaginary Gaussian surface which is right at the boundary of the conductor. It is the boundary of the conductor. So you take this Gaussian surface. If you think the Gauss's law that the flux, electric flux through this imaginary boundary surface, the result of the flux will be the charge inside divided by epsilon 0. But you think that since there is no electric field inside the conductor, because of this is the condition coming from the electrostatic equilibrium, because we know that electric field is always 0 everywhere inside the conductor, that means you will have a 0 flux through this imaginary Gaussian surface, which is just right at the boundary of the conductor. That means the net charge inside the conductor must be equal to 0. Okay, so by using the Gauss's law and by using the electrostatic equilibrium condition, saying that the electric field is equal to 0 inside the conductor, then as soon as you take this Gaussian surface right at the boundary of the conductor, the Gaussian surface, the flux through the Gaussian surface will be equal to 0. The Gauss's law says that this flux is equal to net charge inside the surface divided by epsilon 0. But since the flux is equal to 0, that means the net charge inside the conductor is equal to 0. Okay. So we have this result. The net charge inside the conductor is equal to 0. Whether, even if the conductor has an extra charge or not, whether the conductor is neutral or charged, this is true always. So if you have extra charge, that means the charges must go right at the outer surface of the conductor. Okay. So next thing is what do we have? What is the condition that if I put a metal into a region of space where in this region there is no non-zero electric field, we have some electric fields. Okay. Think about this question. In region of space, we have a non-zero electric field, and into this region we put a metal. What happens? When you can put a metal which has no charge. Okay? Suppose you put a sphere, metallic sphere, which has no charge. As soon as you put this metal onto this region of space, both the electric field lines will be the same. The question. No, because if this is a metal, if this is a conductor, as I said, in conductor, there are free electrons moving inside, right? Well, they are moving, but the net charge is not changing. The net charge is 0. Well, if you put these electrons inside an electric field, when they experience this electric field, they will see a force on them, right? Because whenever you put a charged particle on an electric field, then there will be a force, electrostatic force on that charge, which is in the direction of electric field if it is a positive charge, opposite to the direction of the electric field if it is a negative charge. So as soon as you put this metal, the sum of the electrons, right, will be accumulated on the left-hand side, right? Because electrons, when you put, they will be attracted to the left if the electric field is to the right. This is true. Well, if some of the electrons are going on the left-hand side, then the net charge distribution is changed. In that case, some positive charges must be accumulated on the right-hand side, right? So that the total charge must be equal to 0, right? So as soon as this configuration is there, some of the charges on the left-hand side and some of them on the right-hand side. This is in fact, which is called, what is this called? This phenomena is called the polarization. The charges, when they have no an extra charge on it, the net charge is 0. But some of the charges, electrons, are moving in one side, and when they are moving in one side, since the protons will have no electrons at all around, in that case, on the other side will be plus charges. So this is a polarization. Polarized. The metal is polarized. And then, how, the next thing is how these electric field lines will change. You see, some of these lines, electric field lines, enters to the metal perpendicularly, right? But here at some other places, the electric field lines ends on the surface not perpendicularly, but it has some tangential component, right? It has some tangential component to the surface. If you have this tangential component on the surface, then these charges on the surface will experience electric force, electric field, right? But as I said, the in electrostatic equilibrium, the charges cannot move, because if charges are moving, then the currents will be there on the surface. To prevent this happening, the electric field line, which is coming not perpendicularly to the surface, will change its direction so that it is end up on the surface perpendicularly, right? Right, this distribution happens, the electric field lines will change their direction just around the metal, so that all the field lines ends on the surface perpendicularly. If you think otherwise, if the electric field lines do not end on the surface or emerge from the surface perpendicularly, then there will be current flow on the surface, because there will be net electric field on the surface. This causes the electric forces, and the electric forces will move the charges on the surface. So as soon as you put a chargeless metal inside the electric field, this is how the electric field lines deflect, bends, and also how the charges will distribute it over the surface. At some surface and some part of the surface, there will be net electric negative charges. On right at the opposite, net positive charges. But again, the sum of these charges is zero, because initially you have put a chargeless, which neutral metal, and this fact is still the case. The only thing is the charges are distributed not evenly. For this case, if you put into the electric field, there will be some uneven distribution of the charges over the surface. Okay? Again, electric field is equal to zero. Okay? I remind you that even outside the electric field is non-zero. Whenever you put a metal or a conductor inside an electric field, inside the conductor, the electric field is always zero. Whether it is charged or not, whether it is in an electric field or not, the electric field of a metal inside a metal is always zero. There is no exception. Okay? All right. So once you have, I will finish up quickly. Once you have these charges, which is on the outer surface of a conductor, the next question is, what is the local electric field right on the surface? And the electric field, as you know, must always be perpendicular to the conductor. Now you see that there is another important property in electrostatic. For a metal, if you put a metal into a region of space where there is some non-zero electric field, the electric field lines must always end up on the surface perpendicularly. Okay? This is another statement of the electrostatics that you will face in your problems and in your exams. The electric field is always zero inside a conductor, and the electric field lines are always emerging or perpendicular, ending on the perpendicular to the surface of a conductor. Okay, so you can now calculate, if as long as you know the surface charge density on the surface of a metal, you can calculate the strength of the electric field right on the surface. There's a way to do that. Just pick up a Gaussian surface, a pillbox, a rectangular Gaussian surface, right? And you can keep this side as long as small as you want. Okay, this side length as small as you want, so that one top surface is located just outside the metal, and the bottom surface is just located inside the metal. So the next thing is you calculate the flux through this imaginary Gaussian pillbox. And if you say this has the area top surface as the area A, then it's very easy, because the flux through this area is just electric field strength times A. But what about the Gauss's law says the charge inside must be equal to this flux, charge inside divided by epsilon 0. So the charge inside is just, since this box, it crosses the same area on the surface, the same A, because it's a rectangular surface, and the charge inside is just sigma times A, and this is divided by epsilon 0. This must be equal to the flux. So from this, you can easily get the electric field right outside the surface of a conductor is nothing but the sigma divided by epsilon 0. As long as you know the charge density of the surface of a metal, you can calculate the electric field strength right on the surface of the metal. Okay? And this is the case, and this is another nice way of using Gauss's law to calculate the electric fields. Well, inside, always you have electric field is 0. Okay, this is again the case. Now suppose we have a conductor which has a cavity inside, this empty space, and suppose the conductor has no extra charge on it. So we put a charge, plus charge, Q, into this cavity, into somewhere in the cavity, and the charge is not touching to the inner surface. And of course, because of the point charge, electric field lines will emerge from the plus charge, and they will end on the inner surface normally in a perpendicular direction, that for the reasons that I have discussed earlier. And the question is, what is the inner surface charge density of the conductor? Okay, so this is the question, and although we have no net charge on the conductor, because of the electrostatic attraction of this plus charge Q inside the cavity, we assume that some of the charges will accumulate on the surface, because the other thing is the electric field lines are non-zero right on the inner surface. If there is a non-zero electric field ending on a conductor or emerging from a conductor, then there will be some charges on the surface. There must be some charges on the surface. So for this, again, we will use the Gauss's law. Let's take an imaginary Gaussian surface inside the conductor, so that it contains both the surface, inner surface of the conductor, inner surface of the cavity, and of course the inner charge inside the cavity. And the thing is, this Gaussian surface need not be a symmetric surface, just an imaginary surface. The only condition that this Gaussian surface contains the inner surface and the inner cavity. So if you apply the Gauss's law, first we have to think about the electric flux through this Gaussian surface. But the thing is, whether they are charged or neutral, for all conductors, the electric field inside the conductor is equal to 0. So if there is no electric field lines crossing this inner surface, the imaginary Gaussian surface, not the this inner surface of the conductor, but think about the electric field lines crossing this Gaussian surface, of course it is 0. There is no electric field. The electric field is 0 inside the conductor, so the flux through this Gaussian surface must be 0. Okay, so right away you can write down this flux, or the integral through this surface, is equal to 0. But Gauss' law says if the electric flux is 0 through a surface, a closed surface, then this closed surface should enclose no net charge. The Gauss' law says if there is a non-zero flux, then there must be a net electric charge inside this surface. But if the flux is 0 because electric field is 0, then the net charge enclosed by this Gaussian surface must be 0. But wait a second. We have a plus charge inside the cavity, so there must be some other charges, and these charges should be negative, so that when you add this total charge in the surface, in the Gaussian surface, they must add to 0. Okay, so the only possibility that for these charges, the extra charges, should accumulate on the inner surface of the metal conductor. So the first charge, this in the expression, the inner charge, the Q plus Q, which is we put originally in the cavity, and because the total of the charge must be 0, there must be some extra charge accumulated on the inner surface of the cavity, because there are no charges inside the metal that we have discussed earlier. No net charge should be in the volume. All the charges for a metal must accumulate on the surface. So the inner surface must contain some charges, some negative charges. Okay, so when you equate this equal to 0, then you can find the total charges in the inner metal surface as minus Q. Okay, so but this can be understood by the Coulomb's law, because when you put a plus charge in the cavity, then this plus charge, because of the electrostatic attraction, it will attract the negatively charged electrons inside this volume to the surface. Okay, so this can be understood by whenever you put the plus charge in the cavity, because of the electrostatic attraction, since there are freely moving electrons inside the volume of the metal, they will be attracted to the inner surface. So inner surface will contain negative charge, which has a total of plus Q charge, the strength of the plus Q charge in the cavity. Okay. So the next question is, well, if you attract these free electrons toward the inner surface, what happens to the outer surface? Well, still there are no net charges inside the volume. If also there is no net charge for the metal anywhere, then if you accumulate some of the negative charges in the inner surface, then by the logical conclusion, the outer surface must contain some plus charges, and the totality of these plus charges must be equal to the negative charges in the inner surface, so that it has a no net charge. So the outer surface also must be charged, and this surface has a total charge of the inner charge Q. Okay, so as you see, whenever you put an extra charge into a cavity, into a metallic cavity, this extra charge will reflect itself on the outer surface of the metal.